So, the proportional control action now, right. So, let me start with a first order system, a proportional controller with the closed loop transfer function is k Ts plus 1 plus k. Okay, what is the error? If the reference is a step function, right. So, the steady state error by doing all these calculations, we had done this before also, is 1 over k plus 1, right. The first observation is that the steady state error is non-zero. Okay. I would ideally want it to be 0, but it is not 0 in this case. Okay. Now, what does this proportional control do? Well, the first observation is that the control or the proportional controller, it results in improving the time constant, which means the response is faster. On the flip side, there is a steady state error, right. Now, what we could do is, or just by observing this, say that well, my steady state error can be made smaller and smaller by increasing the value of the gain k. But this may not always be practically possible or even desirable, because I might amplify unwanted signals and so on, right. In some cases of higher order plants, which I will show you an example, increasing the gain could also have the tendency to destabilize the system, right. For example, if I were to look at this root locus, I just keep on increasing the gain, but I just notice that I am now on the verge of instability, right, and that is not desirable. Okay. So, the proportional controller, it improves the response of the system, it also helps improve or lessen the steady state error, but only up to some factor, right. I just cannot get it to 0. Okay. Now, let us see what a pure integral control action do, and this actually go very well with the terms, right. So, integral control action is, well, I have a k, I divide by s, 1 over s has an integral action, right. The Laplace transform of an integral of a signal just was translated to 1 over s of the original signal. Okay. So, the output is again something like this. So, now what is the error? The error is, well, there's something nice happened here, right. So, if I just go through all these computations, the steady state error becomes 0. This we also can see in when we did the error constant analysis, right. Type 1 system, if I am tracking a step, the steady state error is always 0. So, with addition of the integrator as the controller, well, the steady state error is 0, but the system order has increased from 1 to 2, and if we keep on dealing with higher and higher order systems, increasing a pole or adding an additional pole at the origin, which is essentially an integrator, might lead the system to the verge of instability. So, two things to observe here, right. First is proportional control, it improves my transient response, it also helps in reducing the steady state error, but does not eliminate it completely. Integral action, well, I add an integrator to the system, which means I add a pole at the origin, it helps in reducing the steady state error to 0 in this particular example which we were talking, or in this particular case of what happened or what is now the type 1 system. Okay. Higher order systems, it may not always be desirable, right, that I just keep on buying integrators and dumping into the system, it may not work, and we will see why it may not work. So, if I take this example here, well, I need to see, well, how the system looks like now, right. So, the total g of s, if I call this as the open loop transfer function, g of s here is k over s square j s plus b. Okay. Now, okay, let me just say that k equal to 1, j equal to 1, b equal to 1, and I say, well, what is the closed loop system stable? Well, I can actually do the route analysis, but I will do the root locus, right, because now we are fairly familiar with doing that. Okay. So, where are the poles? Well, there is a pole here and a pole here, right, as at s equal to 0 in the sigma and j omega axis or the complex plane. There is another pole at s equal to -1. Now, we do not, I think we now remember the rules of the root locus by heart. So, this guy will go here and we see that these guys actually go this way. We also did this particular example while we were doing the root locus plots, and you see that just adding an integrator here does not help me much, because the system is now becoming unstable. Okay. So, we have to be careful in that way. Okay. Now, what is the effect of disturbances, right, when we use these kind of controllers? So, again let me take this kind of plant here, which is a rotational element with a moment of inertia j and some frictional coefficient b. Okay. Now, let us say there is some disturbance d of s, and I will see what is the effect of this disturbance on the response of my system, and can I get rid of those disturbances by adjusting the value of k. Okay. So, let us say, well, I am just interested at the moment in a step disturbance. So, I want to see what is ys over ds, means the effect of the disturbance on the output y. I can just do this by setting r equal to 0. We learned this, how to derive this transfer function much earlier in the course. So, now what happens is, well, Es because of ds just becomes the negative of y, right. So, I am just, so y goes here, there is no r. So, Es is simply the negative of y. So, I can also see what is the effect of the disturbance on the error signal, right. It is straightforward to see, because what we do when we do this, we just compute this with r of s equal to 0. R of s equal to 0, there is nothing here, y of s enters here. What is E of s? E of s is 0 minus the signal that is coming here. So, E of s is the negative of y of s. Okay. Okay. So, what is the steady state error because of this disturbance? Well, the steady state error, I just do all the formulas, use the final value theorem, and I get that this is minus of t over k. Now, I can take care of this steady state error again by increasing the value of gain k. Okay. Now, what is the effect of this gain k? I am keeping on increasing gain k. Now, where does the gain sit in my characteristic equation? The gain is sitting here. So, k now has some direct relation to omega n, right, s square plus 2 zeta omega n plus omega n s, right, if I just normalize it properly. Okay. So, if k increases, the system becomes more and more oscillatory, right, and for a higher order plants, as we saw earlier, it can also go to the verge of instability. Okay. So, next we see what is the effect of integral action, and we have this integral action in addition to the proportional action, and therefore, we call this a proportional plus integral control action. Okay. So, again ys over ds, I could easily compute it to be this way, and I see that earlier we had stated that increase or introducing an integral action increases the order of the system. So, now I have 3 poles. Okay. With Rs equal to 0, the effect of the disturbance on the error becomes something like this. Okay. Look at this. So, what are things which I have in my control from the control, that is Ti, and I have a k here. Okay. Now, I might be tempted directly to use the steady state error formula from the final value theorem to see what is the steady state error to step disturbance. Okay. So, in order to compute what is the effect of the disturbance on the steady state error while we are using a proportional plus integral control, we might be tempted to use the final value theorem directly, but only thing which we need to be careful is that when we use the final value theorem, we must first ensure that the system is stable, which means I need to choose the k and Ti such that the overall closed loop system is stable, or In other words, the roots of the characteristic equation have negative real parts. J and B are given to me. So, I can just play around with K and Ti. Now, under this assumption that the system is stable or that K and Ti are chosen such that the system is stable, the steady state error, I just use the formula for the final value theorem, is 0. So, the observation here is that proportional plus integral control action helped us in eliminating the steady state error. Now, this is a steady state error due to the disturbance. I will just make it a little more explicit here. Which means the effect of disturbance can be nullified in the system. Now, you may ask a question, why did I not choose only an integral control action? Why do I need K plus 1 over TIS? Why not only this guy, 1 over TIS or K by 1 over TIS? Well, the answer may be found in the previous exercise. So, just try to write down things and then the answer is very obvious there, right. So, to conclude, what we can say is that to eliminate the effect of disturbance, we need both the proportional and the integral terms. The proportional term was not enough as we saw earlier, adding an integral term alone gives us problems which we found in the previous exercise. So, the proportional term here ensures the stability, while the integral terms eliminates the steady state error, right, that we could compute from here. Okay, now let us look at a derivative control action. So, I just have my plant as a rotational element with a moment of inertia j. So, let me say I just start with a proportional control action. I say, why do I even need to use a derivative action? So, I just say, well, put a k here, the closed loop transfer function is k over js square plus k. If I plot the root locus, it will tell me that the poles are always on the imaginary axis as the value of the gain k increases from 0 to infinity, right. So, my response of the system will be purely oscillatory, right, and these oscillations would not die down. Now, I would like these oscillations to be eliminated, right, and we will see how these oscillations can be eliminated. And when I say that the oscillations are to be eliminated, it means I must introduce some damping into the system. So, this system here does not have any damping term, js square plus k, there is no term corresponding to the coefficient s, right, 2 zeta omega n s, right. So, the oscillations can be damped if we incorporate a derivative term in the controller, and incorporation of a derivative term leads to introducing of the damping term in the system. I will shortly show you how that looks like. Okay. So, again take a proportional for plus derivative controller, where the controller now looks like k 1 plus Td of s, and the output from the controller yc of s is so all of these guys. So, I have yc is k e of t plus k Td, now E dot of t, right. We saw this while we were discussing the effect of adding a 0, right. This is actually like adding a 0 to the system, right. So, you have the error and the derivative of the error also. So, the output now is, which was earlier in the case of proportional control only depending on the error, is now also proportional to the rate of the error change, E dot of t. So, what does this derivative term do? This derivative term anticipates a large overshoot with the E dot. Now, how fast it is moving, right? E dot of t tells me how fast my error is moving. So, it anticipates a large overshoot based on the rate, and when the rate of change of the error is too high, it takes a corrective action, right. So, this E dot tells me how fast my error is growing, right, and this effect can be noticed in the improved damping in the system. Okay. So, what is the effect of adding a derivative or a proportional plus derivative term to the plant 1 over Js square, which did not have any original damping? So, the output of the system is now, well, this k, this entire thing is the numerator. Now, look at the characteristic equation or the denominator, j s square plus k times T d times s plus k. Now, this is just a second order system, and we know that for positive values of j, k and T d, the system is always stable. Now, what did the derivative control do? It just added this extra term here, which was absent earlier, right. It added a damping term into my characteristic equation, and this damping term is due to the derivative control action. Okay, now let us combine all these things. We started with proportional plus integral control, and now we later on saw proportional plus derivative control. Now, let us combine all these things together and see what is the effect of each of these things, right. Okay, so let us look at the effect of P plus D plus I on a second order unstable plant. So, let me say that I am starting with a plant which looks like this. Gs is s square minus b, and for b greater than 0, the system is always unstable because my poles are plus minus square root of p. Okay, so the first thing, right. So, in an earlier slide I said proportional control helps in improving the stability of the system. Let us verify if it is true or not. Okay, so I had a Kp here, and with this Kp I am just calling this with the subscript p because I am just dealing with a proportional control action. With this proportional control, the closed loop transfer function is now this one, Kp s square minus b plus Kp. Okay, now is the system stable? Well, at best it could be marginally stable, right, because there is no damping term here, right, but at least starting from this unstable system I could at least get it to a marginally stable configuration by appropriate choice of the value of Kp. Okay. Now, let us add a derivative term. The derivative term, well, what we saw will add some kind of a damping to the system. So, the proportional control got an unstable system to become marginally stable. Adding a derivative term will actually make it what we call also asymptotically stable system, right. So, now the response Ys over Rs has an additional damping term in the system, and for Kp and Kd greater than 0 and Kp greater than b, the system is always stable, right, and therefore I can arbitrarily place the closed loop poles, or given any zeta and omega n, I can design the system for any zeta and omega n. This is what I mean by pole placement, right, because the poles are decided on the values of this. I can place this wherever I want, right, based on appropriate choices of Kd and Kp. Okay. So, this Kp greater than p is also necessary here, right. When this Kp is greater than b, then I have marginal stability. Okay. Now, what happens to the steady state error? Well, the steady state error, I just look at again the formula, and I get that, well, it is, I would like it to be 1 because I am tracking this reference signal. Well, this is not 1, right. Therefore, there is a steady state error in the system. Now, we will see what is the effect of adding an integral term. In one of the earlier slides, we said that adding an integral term eliminates the steady state error. Now, let us add an integral term to this guy. So, I have a Kp, the proportional term, the derivative term, and now I have an integral term. So, the response through this, and I compute the steady state error. So, limit t tends to infinity, this is 1, right. So, what I am, so my R of s here is a unit step, but I am not tracking a unit step here, right. So, my steady state value is Kp minus b. So, I am not computing the steady state error here, but I am just computing the final value. The final value should be 1 because I am tracking a step signal. It is not 1, but depending on Kp and b. So, again appropriate choices of values of Kp we saw earlier also, right. I can keep on increasing the Kp to be a very large value, but that may not help me all the time, right. Okay. Now, adding an integral controller gives me the output as 1, which is what I am tracking, right. I am tracking a unit signal, I am tracking a unit step, right. So, this adding of an integral term eliminates my steady state error. or it means that I can actually track a unit step, right. And so the conclusion is that we have perfect tracking of this unit step. Moreover, we also know that having an integral control action rejects constant disturbance inputs. So, we individually saw what are the effects of adding a p term, the proportional controller, a derivative term useful in adding damping to the system or improving the transient performance, and an integral controller which is useful in improving the steady state performance in terms of the steady state error. Okay. So, just to summarize what we have learned in terms of the proportional derivative and integral control is, well, we could start with an unstable system, second order, and we could stabilize it, right. We could also place the poles arbitrarily or in a way given any choice of zeta and omega n or any performance specifications, I could choose my gains Kp and Kd appropriately so that I achieve those performance objectives. The system has perfect tracking because of the integral control, and what integral control also does, it rejects constant disturbance inputs, right. So, to summarize, we define what are dominant poles and zeros. We by just using MATLAB plots, we saw what were the effect of adding poles and zeros to the system, right. That was for second order systems. We also saw the same thing when I add poles and zeros to an open loop system, what is the consequence on the closed loop system, and we defined three basic control actions: proportional, integral and derivative control action. So, in the next lecture we will see some issues in implementing PID controllers. So, this stands for proportional, integrative and derivative controllers, and we will see slowly define what are lead and lag compensators, what could be the performance specifications in the time and frequency domains, and then correlation between these two specifications if any. Okay, thank you.